All right, so we are going to begin chapter 6 now. So in this video, we will be doing the first section in chapter 6 titled Area Between Curves. So in this section, we are going to talk primarily about if you have multiple different curves on a graph, how do you find an area that falls in between two different functions? So the good news is that there's not any new integration rules today. It's really just one basic definition that we have to be able to apply a couple of different ways. So let me read through the definition here for you, and then I'll kind of write a few things down for you to follow along. It says the area A of a region bounded by the curves y equals f of x and y equals g of x, and then two lines x equals a and x equals b, as long as the two functions are continuous. And as long as one of your functions is always bigger than or equal to the other function for every value in the interval, then the following has to be true. The integral from a to b of f of x minus g of x will give you the area between the two curves. So while that is a very general formula, let's get a little bit more specific. So while all that terminology is great, here's an easier way for you to break it down. If you are going to integrate in terms of x's, which is how this formula is written, this means that you will have to essentially say that the inside of your integral must be your top function minus your bottom function, which means that one function must always be higher than the other function for the entire region you're trying to find. But this can also be related in terms of y. So technically, you could also integrate, and I'll choose two different letters. Let's say C and D. You could also do f of y minus g of y dy if your functions are in terms of y, which we're going to see in a little bit. The way that you'll find the area between them is you will take your right function minus your left function. So one of your functions should always be further to the right than the other function. But really, it's all based off what letters you're given in the problem. So to kind of show you what I mean by this, let's start off with a very simple one. I want you to find the area of the shaded region between the curves y equals 3x minus x squared and y equals x. Now you'll notice on all the graphs today is that I'm not going to label the graphs for you. I'll give you the two functions, but it's going to be your job to know which graph is which. Well, 3x minus x squared is a parabola, so that's going to be this red graph here. So that would be y equals 3x minus x squared. And then the blue line would be y equals x. Since both of these are in terms of x, I'm going to use this first formula in order to set up my area between curves. So if I use this first formula in the purple up here, this would be the integral from a to b. Since we're doing this in terms of x's, you have to use your x-axis for your intersection points. So I can see that the two intersection points between the green region are here. That's at an x value of 0. And then right down here at the bottom is an x value of 2. So there's my parameters. The top function, which is the higher function, is the parabola, which will be 3x minus x squared. And then you'll subtract from that your bottom function, which is just x. And then you need to integrate this with respect to x. And once you get it set up, this is just an FTC Part 2 problem. So I'm going to combine my like terms. So that's the integral from 0 to 2 of 2x minus x squared dx when you combine the x terms. So when you integrate this, you should get x squared minus x cubed over 3 evaluated from 0 to 2. So if you plug 2 into both of those numbers, 2 squared would give you 4. And then minus 2 cubed would give you 8/3. Minus, and if you plug 0 into both of those, you just get 0. Finding common denominators here, I can rewrite the 4 as 12/3 and subtract the 8/3 from that. And this will give me a final area of 4/3. Now, the big thing to note here is that since you are finding area between multiple curves, this has nothing to do with whether you are above or below the axes this time. That only applies when you have one graph. When you're doing area between multiple curves, your area here should always be positive. So everything will be positive in this section. But there you go. There's an example of where it was written in terms of x. We set up our problem and we integrated. One of the challenges that we will run into this section is what happens if you have a choice. So for example, what if you want to find the area of the shaded region between the curves y equals the square root of x minus 1 and x minus y equals 1? Now, as this sits, I can see that one of my curves is already written as y equals something, and the other one is not. If one of your terms is already written in a certain form, it's usually easier to just leave it in that form. So since this is already y equals a function of x, I'm actually going to take the x minus y equals 1, and let's rewrite this in terms of y equals a function. So I would move the x over to give me negative y equals 1 minus x. And then if I divide both sides by negative 1, you should be able to write this as y equals x minus 1. And these are the two functions that I'm going to use to do the area between curves. All right, so going over to my graph to label everything, the blue line is the straight line. So that's going to be my linear function. So that would be x minus 1. And then the red graph is my kind of square root or my curve function. So this would be the square root of x minus 1. Since these are in terms of x, we're going to do our function of top minus bottom when we set this up. So when I set up my integral, we will integrate from a to b. Our intersection points are here and here, and since we're doing x's, you need to use the x-axis for your parameters. So we are going to integrate from 1 to 2. The top function is your square root function, so square root of x minus 1. And then you will subtract your bottom function, which is the linear function. Make sure you put that in parentheses so you can distribute the negative 3. So this will end up being the integral from 1 to 2 of the square root of x minus 1 minus x plus 1 dx. Now, the only challenge here is going to be is that the square root integral is going to be worked a little bit different than the other two. So what I'm actually going to do is I'm going to break this up into two separate integrals. I'm going to integrate from 1 to 2 of just the square root function, because that's going to involve one rule. And then I'm going to add to this the integral from 1 to 2 of negative x plus 1. That's because the second integral, that's just the regular anti-power rule. You can add 1 to the power and divide by the power. But the square root function here, you're going to have to do U-substitution. So what's what we did in the last video. You would let u be your inside function, which is x minus 1, and therefore du would equal dx, and that's a direct sub there. Don't forget that when you do U-substitution, you have to change your parameters, but that's only on this first integral. So you're going to plug your x's in here for your u to change the parameters. 1 minus 1 is 0, and 2 minus 1 is 1. And then I can rewrite this as the square root of u du. Then we're going to add to this the second integral that we are not going to touch. All right, so rewriting that first integral, you will have the integral from 0 to 1 of u to the 1/2 du plus the integral from 1 to 2 of negative x plus 1 dx. All right, so now we can finally integrate. So coming down to the next line, if you integrate the u function, you would add 1 to the power to get u to the 3/2, and I'm going to multiply by 2/3. And we'll evaluate that from 0 to 1. And then I'm going to add to this. If I integrate the second function, that's negative x squared over 2 plus x evaluated from 1 to 2. All right, so plugging my parameters in. On the first one, if I factor that 2/3 out and then just plug the 1 and 0 in, you will have 1 to the 3/2 minus 0 to the 3/2 plus, if you plug the 2 in, that would be a negative of 2 squared over 2 plus 2. And then subtract from that, you need to plug 1 in, which is negative 1 squared over 2 plus 1. All right, little arithmetic here. So you're going to end up getting, so 1 to the 3/2 minus 0 is just going to be 1. So that whole first piece just becomes 2/3. And then inside of this bracket, if I do my order of operations, you should get, let's see, that's negative 4 over 2, which is negative 2, plus 2. Well, that's really nice. That's going to end up canceling. And then minus, you get a negative 1/2 plus 1. Negative 2 plus 2 goes away, and you are going to be left with 2/3. Negative 1/2 plus 1 is 1/2. With a negative out front means you need to subtract a half from that. And when you find common denominators here, you should be able to write this as 4/6 minus 3/6, which gives you a final answer of 1/6. So once again, they're not going to always be straightforward. This one was a little bit trickier because part of your integration was U-substitution. The other one was regular integration, FTC part 2, and then you had to go through the idea of putting them together. But that little bitty area up there is 1/6 of a unit. All right, so now let's do a couple where you have to do this in terms of y. So we're not going to do top minus bottom anymore. So example number 3, find the area of the shaded region between the curves x equals y squared minus 4y and x equals 2y minus y squared. All right, so both of these are already written in the form of x equals a function of y. So you just need to make sure that you label them correctly. So the blue graph is actually a y squared function opening to the left, which is the negative direction. So this would have to have the negative y squared on it. So that's going to be 2y minus y squared. And then the red sideways parabola is opening to the right, which is the positive direction. So this would have to be, y squared. Go away. There we go. Y squared minus 4y. So when we set this integration up, so we are going to still do the integral from a to b, but since we're doing this in terms of y, when you look at your two intersection points, you have to use the y-axis to help you. So the lowest point would have a y value of 0, and the highest point would have a y value of 3. Then it's going to end up being right minus left. So I would take my right function, which is 2y minus y squared, and subtract from that my left function, which is y squared minus 4y. Distribute the negative through. So this is the integral from 0 to 3 of 2y minus y squared plus 4y dy. And then put your common terms together. So this would be the integral from 0 to 3 of 6y minus 2y squared dy. So you've done with your simplifying. Now you can integrate this like normal. So this would become, after simplifying, 3y squared minus 2/3 y cubed, evaluated from 0 to 3. All right, plug your 3 in, and you should end up getting 3 times 3 squared minus 2/3 times 3 cubed minus, plugging 0 into both of those is just going to make both of those terms go away. So simplifying the first parentheses, 3 squared is 9, and 9 times 3 is 27. Minus 2/3 times 27. which would be 27 minus 27 divided by 3 is 9, and 9 times 2 is 18, which this is going to end up giving us 9. So the area between those two curves comes out to exactly be 9. So once again, if you're doing functions of y, it's right minus left, but you have to do your parameters in terms of y's. Let's look at another one that's very similar. So what if you have the functions x equals y squared minus 2 and x equals e to the y? And this time, since they don't intersect very nicely, I do sometimes will give you the parameters I want you to use. I want you to go between -1 and +1 on your parameters. All right, so the blue and the red graph, one of them is an exponential function and one is a y squared. So I can tell that the red graph kind of looks like a sideways parabola. So I know that this red graph is going to be the y squared minus 2. And then the blue graph looks like a natural log function actually, but since it's an e to the y is actually the same thing as a natural log function because it's the inverse of it. So this is your e to the y function. Since both of these are in terms of y, we're going to use right minus left when we do this. So the area between the two curves is the integral from a to b. So remember, I gave you the parameters. I want you to go between -1 and 1. The right-hand function is the e to the y, minus the left-hand function is the y squared minus 2. Distribute that negative through, and we're going to go integrate from -1 to 1 of e to the y minus y squared plus 2 dy. We can integrate all three of those terms. So the integral of e to the y is still e to the y minus y cubed over 3 plus 2y evaluated from -1 to +1. If you plug 1 in, this would end up being e minus 1/3 plus 2. Plugging in 1 is usually pretty easy. Minus, if you plug in -1, let's see, that's e to the -1. That's going to be a -1 on top, so it actually becomes plus 1/3 and then minus 2. Distribute that negative through, so it's e minus 1/3 plus 2 minus e to the -1 minus 1/3 plus 2, which you can put a few of those terms together. So you'll have an e and an e to the -1. Those just stay the same. Then you'll have a minus 2/3 when you put the thirds together, and then a plus 4. Getting common denominators should give you e minus e to the -1 minus 2/3 plus 12/3, which gives us a final answer of e minus e to the -1 plus 10/3. And that is the exact area between those two functions. For the first time, you notice that both of our terms were very different. One was an exponential function and one was a polynomial function. So it kind of makes sense that our answer didn't combine very nicely at the end, but that's okay. Like I said, that is going to end up being our area between the two curves. All right. And now something I want to mention, and I haven't done any of it yet, but at the very end of the last video, I talked very briefly that sometimes over the next few sections, we would run into symmetry, all right? And I want to show you an example in this video where symmetry can be very helpful. So if you look at this, it says find the area of the shaded region between the curves y equals x squared and y equals 32 over x squared plus 4. All right, so in this case, we are going to label our graphs like normal. So this green graph looks very familiar. That is going to end up being your x squared graph. And even if you don't know what the 32 over x squared plus 4 looks like, it's kind of a giveaway by default that this is 32 over x squared plus 4. Now, what I want you to recognize here is that if you look on both sides of the y-axis here, it's very easy to see visually that this side of the gray graph is exactly the same thing as the other side. The reason that's important is because if you don't notice the symmetry, you would have to integrate from -2 to +2 in this case. But if we were to just integrate half of this, so if you just found this area right here, then you could find that area and double it, and this would allow you to go from 0 to 2, which makes one of your parameters a lot easier. So let's do it that way to see how it works. So setting your area up. So if I wanted to find the area of the right-hand side of this, this would be the integral from 0 to 2. So we're only going from here to here. It's in terms of x's, so you have to do your top minus your bottom. So this would be 32 over x squared plus 4 minus the bottom, which is x squared. All right, so we're going to have to, let's see, we're going to have to do a little factor. We're going to do a little factoring here. Oops, sorry, dx. I'm actually going to break this up into two separate integrals. So I'm actually going to write this as the integral from 0 to 2 of 32 over x squared plus 4 minus the integral from 0 to 2 of x squared. Just because both of these integrate very differently, and one of them I may need to factor a little bit, all right? So the first one, what I'm going to do is I am going to factor the 32 out front to make this 32 times the integral from 0 to 2 of 1 over x squared plus 4 dx minus the integral from 0 to 2 of x squared dx. Now, this looks very similar to an inverse tangent problem, but we're going to have to make it an inverse tangent problem, unfortunately. So if you remember from a previous section, we know that the integral of 1 over x squared plus 1 dx is going to be the inverse tangent of x. So what we need to do here is we've got to figure out, okay, how could we rewrite this in order to make it a little bit nicer? All right. So what I would do, let's see how we want to do this. I'm trying to think, there's two ways to do this. I'll make sure I do it the easiest way for you. So what we could do here is we could rewrite the bottom here. So we have to end up kind of manipulating this into something that looks more like this. So the biggest problem here is going to end up being that we can't have a 4. We need that to be a 1. So here's going to be kind of some cleverness. I need to factor a 4 out of the bottom. Okay, it's going to be a little weird. If I factor a 4, oops, I mean to change to red, my apologies. If I factor a 4 out of the bottom, so out in front of the integral, it looks very normal because it makes the 4 a plus 1. But what it does is that it changes the x squared into an x squared over 4. And I know that looks very, very weird. It's okay. Minus the integral from 0 to 2 of x squared dx. Now, notice that x squared over 4 doesn't match either. We need to make this something a more general term squared. So 32 divided by 4 is going to give me 8. I'm going to integrate this from 0 to 2. And then what we're going to do here is we are going to rewrite this as x over 2 all squared. Because what I'm going to try to do is I'm going to set up a U-substitution to turn it into an inverse tangent. So even though it looked like an inverse tangent, and it is, you have to go through the manipulation to get it into the perfect form so that you can actually use it. All right, minus the integral from 0 to 2 of x squared dx. So on that first integral, I'll do the u substitution over here. I'm going to let u equal x over 2, and I'm going to let du therefore be 1/2 dx, which means that 2 du is going to equal dx. When I do u substitution for the first integral, this would be 8. Now you're going to have to change your parameters on the first one. So if you plug those into your u, 0 divided by 2 is 0, and 2 divided by 2 is 1. And then this becomes 1 over u squared plus 1 times 2 du. And then remember, that second integral I have not touched yet because we know how to integrate that. I'll do that once we get through doing the harder part. All right, this extra 2, what I'm going to do to save myself some writing, I can bring this 2 out front and make it a 16. And now you see this matches exactly my inverse tangent integral. So I can now rewrite this as 16. And then if I integrate the inside, this is the inverse tangent of u. We're going to evaluate that one from 0 to 1. That's the hardest part of this problem, is just manipulating that first problem. And now that I've started integrating, now I can do the easier integration, which is x cubed over 3 evaluated from 0 to 2. So plug your values in. This would be 16 times, this is going to be the inverse tangent of 1 minus the inverse tangent of 0 minus, if you plug 2 into the second one, that's going to be 8/3 minus 0. All right, so let me scroll down a little bit. You need to know your inverse trig values. So the inverse tangent of 1 is going to be pi over 4. All right, and then you're going to end up having minus the inverse tangent of 0 is 0. And then you get a minus 8/3 on the end. And then you end up multiplying by 16 through, and that would end up giving you 4 pi minus 8/3. And that is the exact area in this problem. Or it would be, but remember, all we did was find the area of half. So at this point, there's two different ways that this can be done. This area we just found was the area to the right-hand side. So you have two options here. At this point, all you have to do is double your final answer. So down here at the very bottom, I am now going to multiply all of this by 2, both terms. And that would give me a final answer of 8 pi minus 16/3. Now, what some people suggest, and I may start doing this going forward, I want to do the area by itself first, is that what some people prefer to do is to put the 2 in front of the original integral. The reason that I sometimes don't do that is because if you start breaking things apart, you have to be very, very careful, but really it's up to you. So either, no matter what you do, whether you put the 2 at the beginning or whether you double your answer at the end, it's all the same thing in the end. Whichever way you do it, your final answer should be 8 pi minus 16/3. So a little bit different manipulation. So when inverse trig is not set up perfectly, we now can see how we can manipulate it to make it work. All right, so the last thing in this section we're going to talk about, because we've talked about area between curves, is we haven't seen any examples of where the curves switch top minus bottom throughout the process. So for the last two things we're about to look at is that, and I'm going to jump straight down to the picture really quick, is as you go from A to B, what if the top and bottom switch either once or multiple times? So as you can see on this diagram, this red graph goes from being the top function in this interval, then it goes to the bottom function, and then it goes back to being the top. The challenge to this one is that you're going to have to be able to do all three areas separately and then put your final answers together, which makes it a lot more difficult because it's a lot more work. But unfortunately, not every pair of functions you get will always be simply top minus bottom throughout. So a way that we can denote this, and how they'll denote this on the homework, is that if you're trying to find the area between curves that alternate, this can be expressed as the integral from A to B of the absolute value of f of x minus g of x. And what that does is that it's the notation to where you have to make sure you alternate what's top and what's bottom. So in this little piecewise function, what this is telling us is that, once again, it's still going to be top minus bottom, but now you're going to have to flip-flop what the top and bottom are throughout. You could also do this in terms of y's and do right minus left. I'm not going to do that to y'all in this section because since these are a little bit trickier and a little bit more complex, I'm going to stick with just terms of x and do top minus bottom. So what we're going to look at now is we're going to look at a couple examples that alternate throughout, and we'll see how to approach those. So here is the first one. Example number 6. I want you to find the integral from 0 to pi over 2 of the absolute value of sine x minus the cosine of 2x. All right. So in this case, here's your diagram. And as you can see, the green graph starts at 1 and is on top, and then it becomes your bottom function. And based on the parameters they're given us, I know that we are stopping at pi over 2. Your blue graph starts off as the bottom function and then becomes the top function on the second part. First thing to figure out is which one is which. Well, I know that sine functions always start at the origin, so that means that this blue graph is going to be your sine function, and therefore this green graph is your double angle of cosine function. The other challenge here is that if you look at the graph, you've got to figure out where they swap from being top and bottom to vice versa. But I didn't label that very clearly. And while you may think it may be 1/2, and it might be, that's not always guaranteed when it comes to trig. So what I would do if I was you is I would figure out where these two functions equal each other. So I would say that sine of x needs to equal the double angle of cosine, because wherever they intersect, that is where they're going to equal each other at. Now you need to use an identity here. So from your double angle of identities, the double angle of cosine can be expressed as 1 minus 2 sine squared of x. In order to factor this, I'm going to move both of these terms on the right over to the left so that I can write this as 2 sine squared x plus sine x minus 1 equals 0. This can be factored. So we're going to end up having 2 sine x and sine x, 1 and 1, and then it should be minus and plus equals 0. And then we're going to set both of these equal to 0, and then I'll scroll back up a little bit. So 2 sine x minus 1 equals 0, and sine x plus 1 equals 0. When you solve both of these, this would be sine x equals 1/2, and sine of x equals -1. But once again, I don't need all of those answers. Since I know this intersection point has to occur between 0 and pi over 2, it has to occur in quadrant 1. And looking down here, sine can't be negative in quadrant 1, so I'm not worried about that one. Sine can be positive, so you have to ask yourself, where in quadrant 1 is sine 1/2? That's going to occur at pi over 6. So therefore, I can now break up my original integral into its two unknowns. So this will end up being the integral. We're going to go from 0 to pi over 6. The first section, you got to do top minus bottom. So that would be the double angle of cosine minus the bottom, which is sine, dx. And then I'm going to add to this the integral from pi over 6, and we're going to stop at pi over 2. And now you flip-flop them, and you now have to do sine of x minus the cosine of 2x dx. Now here's where it gets fun. You're going to have to break this up into 4 different integrals because the double angle of cosine and a sine function are both integrated differently on different, and you have to adjust them, and then you have to do it for different parameters. So I would actually rewrite this as the integral from 0 to pi over 6 of cosine 2x minus the integral from 0 to pi over 6 of sine x plus the integral from pi over 6 to pi over 2 of sine x, all right, minus the integral from pi over 6 to pi over 2 of cosine of 2x. The second and the third integral, those are perfectly fine. We know how to integrate those. But both of your double angle of cosines, you're going to have to do U-substitution on. The good thing is that they are both the same U-sub. So I'm going to let U equal cosine 2x. And therefore du would be 2dx. And du over 2 is your dx value. Now, on both the first and the fourth integral, you will have to also change your parameters by plugging them in for x and changing them throughout. So on the first parameters, if I plug in 0, 2 times 0 is 0, and 2 times pi over 6 is pi over 3. And this would be the cosine of u times du over 2. Minus the second and third integral we're not going to touch because we know how to integrate those. Give me a second to write those down. Minus, now you have to do the same U-sub but different parameters this time. So if you plug in pi over 6, your new lower parameter becomes pi over 3. And then plugging pi over 2 in makes your new upper parameter pi. And then you also get cosine of u times du over 2. All right, so these can all be integrated now. So let's scroll down a little bit. There we go. So we are going to end up having, factoring the 1/2 out front, the antiderivative of cosine is the sine of u, which we're going to evaluate from 0 to pi over 3. Minus the antiderivative of sine is negative cosine of x, evaluated from 0 to pi over 6, plus the antiderivative of sine is negative cosine, evaluated from pi over 6 to pi over 2, and then minus the antiderivative of cosine u is sine u. Don't forget the 1/2 like I almost did. That 1/2 comes out front. And you evaluate this from pi over 3 to pi. So you've got a bunch of numbers coming here. So here we go. This is going to be 1/2 times. If you plug in pi over 3, the sine of pi over 3 is root 3 over 2, minus the sine of 0 is 0. Bringing this negative out front turns this into addition, and you just have a cosine. Cosine of pi over 6 is root 3 over 2, minus the cosine of 0 is 1. Bringing this negative out makes this a minus, and then cosine pi over 2 is 0, minus the cosine of pi over 6 is root 3 over 2. Minus 1/2 times sine of pi is 0, minus sine of pi over 3 is root 3 over 2. All right, so writing everything out that I can, you should end up with a root 3 over 4 plus a root 3 over 2 minus 1 plus a root 3 over 2 and then plus a root 3 over 4. All right, so putting together your root 3's, let's see, root 3 over 4 plus root 3 over 4 is going to be simplified into root 3 over 2. Root 3 over 2 plus root 3 over 2 is just going to be a root 3 with a minus 1. And then a half a root 3 plus a full root 3 is going to give you 3 root 3 over 2 with a minus 1. And that is the area between both of those curves. Like I said, the challenge, though, is we had to write it as 2 separate integrals, and then that became 4 different integrals because they had different integration techniques. So when part of your integration is U-sub and part of it's not, you have to individualize those integrals in order to keep them all organized. So be careful. It's a lot of little steps there. And make sure you're keeping track of where the top minus bottom happens. So let's do one more that's not trig, and also one that's a little bit easier to recognize where it splits up. So what is the integral from -1 to 1 of the absolute value of 3 raised to the x minus 2 raised to the x dx? Now looking over here at your graph on the left, these are both exponential functions, but they look very similar. So making sure you get which one is which is very vital at this point. I'm going to focus for everything bigger than 0, because what I know is that the bigger that the base is, the faster that numbers will get larger. So if you look, once you pass the 0, the red graph gets larger a lot faster than the blue graph does. So that means that this red graph has to be 3 to the x, and this blue graph has to be 2 to the x, just on how fast it's getting up the y values. Now, the good news is that I only want you to go between -1 and 1, and it's very clear to see that they switch at 0. So what I would do here when I broke this up is I would write this as the integral from -1 to 0. The blue graph is on top, which would be 2 to the x minus the bottom function, which is 3 to the x dx. Then I would add to this the second integral, which I'm going to go from 0 to 1. Now the red graph is on top, so this would be 3 to the x minus 2 to the x dx. You don't have to rewrite anything, and you can actually leave these integrals together because all of this integrates directly. You don't have to do any kind of U-subs here. So going from left to right, the integral of 2 to the x is 2 to the x over the natural log of 2 minus 3 to the x over the natural log of 3, evaluated from -1 to 0. And then I'm going to add to this the same integration just backwards. So 3 to the x over the natural log of 3 minus 2 to the x over the natural log of 2, evaluated from 0 to 1. Start plugging your parameters in. So if I plug 0 into both of these, raising a number to 0 is just going to make it 1. So this is 1 over the natural log of 2 minus 1 over the natural log of 3 minus, and then if I plug my negatives in, -1 in, sorry, this would be 2 to the -1 over the natural log of 2 minus 3 to the -1 over the natural log of 3. Then you're going to add to this, and now you do your integration values of the second one. So plug 1 in. That would be 3 over the ln of 3 minus 2 over the ln of 3. All right. Minus, if you go back and plug 0, that would be 1 over the ln of 3 minus 1 over the ln of 2. So a lot of this stuff doesn't simplify. Really, the only thing that I noticed so far is going to end up being the second set. So let's go through and write everything out. So I would actually write this as 1 over the ln of 2 minus 1 over the ln of 3. These 2's and 3's to the -1, you can flip those down to the bottom and make them positive. So I would actually write this as minus 1 over 2 ln of 2 minus 1 over 3 ln of 3. So just bring those to the bottom and make them positive. And then plus 3 over ln 3 minus 2 over ln 3. Oh, sorry, ln 2. I messed that up in the first one. I'm sorry. That should be an ln 2 right there. Oopsie, sorry about that. So 2, 2. And then minus 1 over ln 3 plus 1 over ln 2. All right, so let's see. It looks like you have a 1 over ln 2, a 1 over ln 2, and a -2 over ln 2. All three of those actually cancel each other. So goodbye, goodbye, and goodbye. All right, then we can, so let me double line. So then I can put together this term and this term, because those are both -1 over natural log 3's. So those would go together as -2 over the natural log of 3. Actually, sorry, there's another one. You can also add the 3. So a -1, a -1, and a +3 makes that a +1 over the natural log of 3. Then you've got -1 over 2 ln of 2 minus 1 over 3 ln of 3, because those don't go together yet. So the last thing you can really do here is we could put these ln of 3's together if we got them to have common denominators. So I would put a 3 on the bottom of the first fraction, which means I need to put a 3 on top. And then I can put these together, all right? And that would end up being, so let's see. So that would end up being, so 4 over 3 ln of 3 minus 1 over 2 ln of 2. That is your final answer. So that one actually wasn't as bad. It's a lot of little details there that we want to make sure you don't mess up, because there's a lot of ln's and 3's and ln's of 2's that all look the same. Remember, you can't combine those. They must stay separate. But also back to the beginning, when you're doing these absolute value area integrals, it's always top minus bottom, and you have to be aware of where they switch. So that ends the video for section 6.1. So that's area between curves. Starting in the next video, we will get into the idea of volume, and we're going to spend the next 2 videos or 2 sections going over volume of functions rotated around different things.